Hello everyone. In this session, we are not only going to implement the k-means clustering model using scikit-learn, but we are also going to understand how we choose the right value for number of clusters. That is a value for k. So before we begin with this particular coding exercise, let us actually look at the different steps that are involved in the k-means clustering process. The very first step here is to choose the number of clusters, that is a value for k. The second step here is randomly selecting the cluster centroids C1, C2 and C3 here. It need not be a random selection always. We can also implement sophisticated algorithms like kmeans++, where we are choosing the cluster centroid C1, the initial cluster centroid C1 randomly, and the later cluster centroids like C2 and C3 purely based upon probabilistic approach. Let's say that this is your cluster centroid C1 which is chosen at random, and the points that are very far away from C1, that is this particular point, will receive a higher probability for it to be chosen as your subsequent cluster centroid than a point which is very close enough to C1. I believe that you have gained a proper intuition on how the cluster centroids C2 and C3 are assigned in case of k-means++. Okay. So once the cluster centroids are actually identified, either by using random selection or by using k-means++, we're now moving to assignment step where we are computing the distance of a given data point xi with respect to all other cluster centroids C1, C2 and C3, and we'll try to identify which of the distances is minimal. So we understand that D3 is minimal for the given example, and hence we assign a cluster label of 3 to this particular data point. Likewise, we consider every single data point and compute distances with all other centroids and try to assign labels to all of these points. So once we assign labels to all of these points, we have newly formed clusters now. So these are the newly formed clusters. But these centroids are no longer valid. So in step number 4, we are now going to recompute the centroids. That is, take the mean of all of these data points, mean of coordinates of all of these data points, so as to obtain your new cluster centroid C1, C2 and C3. So in step number 5, you are going to repeat step 3 and 4. Right? So once you have newly formed clusters with updated centroids, you are going to reassign the labels again because you have new centroids now. So once assignment is done, you're also going to update the cluster centroids again. This process is iterative. Step 3 and 4 are basically iterative in nature till we obtain convergence. So what is the convergence criteria here? When the centroids do not change much, iteration after iteration. So you observe that the centroids are not moving in any other direction. So they are staying where they were actually in the previous iteration. That's a point of convergence. Or the points remain the same in the clusters. So I'm not adding any of the new data points to this cluster, not excluding any of the existing data points from the cluster. Then also it is said that we have reached convergence. Or the maximum iterations that we have set is reached. When any of these criteria is met, we call it a convergence. Then we stop the iterative process. I believe that you have gained a proper intuition on how k-means clustering model works in an algorithm standpoint. Now let us look at implementing it by considering a particular example data. I'm now going to load this particular data set called iris flower data set. I'm going to consider a very simple data set so that we are conceptually understanding it better. Later, we'll look at considering complex real world data sets and try and solve those problems. So we are going to load this iris flower data set and assign this to a particular data frame called data. So we can also inspect how the data looks like. So we clearly know that there are 5 different variables or columns involved here, out of which 4 are numeric and 1 is categorical in nature. So I do want to get only numeric features here. So I want to use numeric features in my k-means clustering model. So that's one of the criteria, as you know. I'm going to get all of the numeric features now. So I'm going to make use of this method called select dtypes and include only int64 types and float64 types here. Obviously, I'm referring to all of these columns. All these columns are now stored in the form of a list after I invoke this method called toList. I can call this as numeric variables, and let's print the numeric variables as well now. I'm going to later assign this to a new data frame called data in by providing the numeric variable list that I have created within the subscript notation. You can inspect the shape of it, shape of the actual data frame as well, so as to understand that one categorical feature is excluded now. So for whatever data that I have now created, for whatever numeric data that I'm considering for creating k-means clustering model, I should be looking at normalizing the data since we are computing the distances. Any distance based algorithm needs to have the data to be normalized. We already have assessed the impact of not normalizing the data, especially when you are computing the distances. So let us import min-max scalar from pre-processing module. So min-max scalar is what we'll import. We'll also import kmeans class from cluster module. I have imported the necessary classes and the necessary packages here. I'll reload the dataset data in. And now I'm going to consider this particular min-max scalar and try to create an object associated with it. Call it a scalar. There's a typo here, scalar. I'm going to make use of this scalar object and apply fit transform onto my complete data and reassign this to X data here. Now let me check the shape of it once we actually normalize the complete data. You can also inspect the min value and max value for any of these particular columns that you are having within your data. The min-max scalar basically scales your complete data into the bounds of 0 to 1. You can essentially go about checking what could be the maximum value, but I'm leaving it as an exercise to you to inspect the data thoroughly. Anyhow, once we have looked at normalizing the data, we are going to consider this normalized data in order to create your k-means clustering model. So we are going to leverage this class called kmeans that we already have imported and look at what could be the parameters that we can pass. So the default cluster centroid initialization algorithm is kmeans++. So we need not explicitly state it. So this basically has number of clusters as well, which we are supposed to provide. And random state is yet another parameter that I'm planning to set so as to make sure that the data points that are considered for this algorithm are reproducible. And then the max iters is set to 300 here. So I'm just leaving it as is. So now I'm going to assign this to a particular object called model. I'm going to fit it onto the X data. So once I fit this particular model onto X data, we now have access to something called inertia. So inertia is going to be within cluster sum of squared distances. So how do we actually measure how good of a clustering model that we have created? So that's by using a metric called within cluster sum of squared distances, WCSS. So what does this mean? So this actually also means inertia here. So inertia or within cluster sum of squared distances is nothing but you compute all of these different distances in between a particular data point with respect to cluster centroid. So all the distances that you have computed here, that is distance of every individual data point within the cluster with respect to the cluster centroid, are now computed. And whatever differences that I obtain, I'm now squaring them. I'm squaring all the differences that I observe in between a particular data point with respect to its cluster centroid, squaring them off in order to nullify the effect of negative values. And then obviously I'm going to take a sum of all of this for different clusters that I'm having. Let's consider a case where you are basically having 3 different clusters. Now you compute the within cluster sum of squared distances in this particular cluster called cluster 1 and WCSS for cluster 2, WCSS for cluster 3, or I can call it as sum of squared distances. The naming convention is left up to me. And once I have all of these distances or sum of squared distances calculated, I take a summation of all of this. Like instead of looking at this particular formula, let's consider that we are actually considering summation of I equal to 1 to k and then summation of xi belonging to ci. Then obviously I am going to look at xi minus mu c whole square. Right? So what am I doing here? For all of the data points within a given cluster, so for all the data points, for all xi's within a given cluster, I am essentially looking at taking the sum of squared differences or sum of squared distances with respect to the cluster centroid here, right? And then whatever WCSS values that I obtain for every individual clusters is again summed up. I'm summing up. If you look at the outer summation here, That essentially means that you are summing up the sum of squared distances that you obtain for every individual cluster here. So this particular metric is called inertia. So inertia is going to help us explain how well of a clusters that you have defined. So how compact clusters have you ended up creating? So that's the whole idea behind it. So once we have understood clearly about inertia, so we are now capturing inertia for different values of k. So let me actually have an iterative for loop here, where I'm just trying to iterate over a range object from 1 to 10. I'm going to evaluate different values of k and replace this arbitrary value of 3 with k, and then create an empty list called WCSS list right before this iterative for loop. And I'm going to append this list with whatever inertia that I have captured here so far. I run this whole code and now I have the complete list of inertias for different values of k. I simply go about generating a plot by creating figure and axis objects using plt.subplots function. So ax.plot is going to help me generate this plot that I'm looking forward for, where on x-axis I observe this varying values for k, that is a range object starting from 1 to 10. 10 is being excluded, as you know. And the y-axis will hold whatever WCSS values that you have captured in the above step. I'm also providing a marker as solid circle, and setting an x label. X label here is going to be k, the number of clusters. I'm also providing an arbitrary font size of 14 here. Set the y label as well. So y label here is going to be inertia or within cluster sum of squared distances. And finally, plt.show is going to help me generate the plot altogether. So we clearly can perceive that for k equal to 1, we observe a very high value for inertia, which is bad, right? And whenever you have an arbitrarily larger value for k, let's say that you are having k value as 20, just considering some random example, then you might end up having a negligible value for WCSS or inertia, right? So why do we have that? So let's say that you are having 20 different data points within your coordinate space and having number of clusters as 20. That essentially means that you are creating a cluster for every single data point, which is not right at all. So obviously WCSS will result in a value of 0 because distance of this point with respect to the point itself is going to result in a value of 0, right? So obviously this is not a right choice. So WCSS or inertia value has to be minimal, but not that minimal where you end up creating large number of clusters. So having large number of clusters essentially means that you are generating an overfitted model. So having very less number of clusters essentially means you are creating an underfitted model. So this elbow point that where we are observing is the more appropriate value for number of clusters. Since your next value of k, we do not observe any significant change in inertia value. If you look at the delta here, the delta is very small. The delta between the inertia value of at k equal to 2 versus k equal to 3 is significant. And hence we choose this particular elbow point to be the right or optimal value for number of clusters here. Okay? So this is how you finalize the value for k. So once you basically look at finalizing the value for k, you recreate the model object by considering the optimal value for k now. The optimal value for k that we have tried to identify from the visualization that we have generated above is going to be 3. And we'll also generate the predicted labels, which are nothing but the cluster labels. I'm going to assign this to data in, provide a new column called cluster underscore label. I simply run this particular code and now basically go about looking at the value counts associated with the different cluster labels that I have ended up creating. So there are 61 data points that are classified to cluster label 2, 50 of them categorized to 0 and 39 of them categorized to 1. You can also derive the summary statistics pertinent to each one of these cluster labels by simply doing a group by on cluster label, right? And essentially reference all the given numeric values that you're having and draw a mean of it. So we clearly can understand that this particular cluster label, cluster label 2, generally has a higher petal length and higher petal length as well as higher petal width. But if you look at this particular group where cluster label is 0, you're having low petal length and low petal width. So this is a clear distinction that we are observing. And cluster label 1 has got a higher sepal length than the other two groups that we have tried to identify. So we are trying to observe the properties of these different clusters. So every single cluster will have all of its data points with more or less similar properties associated with themselves. So one of the biggest drawbacks of this metric that we have discussed so far, that is inertia within cluster sum of square distances, is basically that it only considers intra-cluster distance and it actually doesn't consider about the inter-cluster distance. So it always bothered about how good of a clusters that you have created or how compact the data points are within a specific cluster, right? But it never bothered about the distance between the clusters. So Silhouette coefficient is one of the other metrics which not only bothers about intra-cluster distance but also bothers about inter-cluster distance. So that's what is our next subject of our discussion. Silhouette coefficient is what we'll be discussing in our subsequent session, where we'll also compute the Silhouette coefficient for varying values of k and try to identify the optimal value for k. It's not always a good practice to only rely on elbow method because of its own disadvantages that we have just spoken about. Okay, so that's all in this particular session, and thanks for watching.